Hello, everyone. So with this video, we start reviewing the basic data structures. Actually, in the upcoming a couple of more videos, we will be reviewing the arrays, linked lists, stacks, queues, trees, and graphs. And before starting this review, I would like to talk a little bit about what a data structure is. When someone asks you what is an algorithm, that is not a very difficult question to answer. You can say that, okay, so an algorithm is a step-by-step procedure. Okay, good. But what if you are asked to answer what is a data structure? Then it is not that much easy because data structures are very much coupled with the algorithms, and without an algorithm, it's hard to define a data structure. So that is why I prefer to use an analogy here. So let's assume the data is the water, okay? And in daily life with water, we do a lot of tasks, right? So we give water to plants, we give water to animals. So we use it for cleaning, we use it in preparing our meals, many things. You can do many things with water. However, each task requires a different handling of this water, right? Similarly, if you think data as water, you would like to handle your data in the most appropriate way according to what you would like to achieve. Okay, so according to the computation, I would like to represent my data in the most appropriate structure. Following this water data analogy, so let's assume you would like to feed your cat. To feed your cat, it's better to put water in a white dish, right? But if you would like to give water to your bird, maybe it would be better to put this water in another cup that will be more appropriate. Okay, so if this bird is a stork with a long beak, then it would be better to put the water in a glass that is long and narrow. Okay, so that would be better. Okay, so moral of the story, if data is water, then data structure is the cup that you put that water in. And the aim of using that cup and the aim of using that data structure is to help the computations to be run more effectively, more efficiently. Okay, so that is the general data structure definition. And we start with the most fundamental data structures, arrays and linked lists. Actually, all data structures are based on arrays or linked lists, because there are only two ways to maintain your data in memory. When you would like to keep your data in memory, when you would like to represent your data digitally. So if you maintain your data as a contiguous block, we call this an array. Or if you maintain your data with separate blocks in the memory, not a contiguous one, so that's called a linked list. Okay. So to understand the arrays and linked lists, I believe it is crucial to have the basic understanding of two concepts. The first one is the locality of reference principle. And actually, based on this locality of reference principle, during the development of these computers, so people decided on how to move data between different levels of memory. Okay, so then I would like to just quickly review those two concepts. The first one is the locality of reference. From the very early days of computing, so the programmers noticed two facts. The first one is, if you are accessing a memory location, if you are accessing a specific data, then it is more likely that you will be accessing that data, you will be accessing that memory location again very soon. So that is called locality in time. If you access something, it is highly probable that you will be accessing the same data very soon in the future. So that's the temporal locality. And the second one is the locality in space. Locality in space means, so if you're accessing a data point, again, it is more likely that you will be accessing the data points near to that recently accessed item. So if you are accessing, let me say, the third position in an array, you may assume that you will be accessing fourth, fifth, sixth, or first, second positions, again, near time. So that is called the locality in space. If you are accessing a position, you will be accessing the items near to that position. Okay, so these are the two principles. Okay, and based on those two principles, actually, there appeared a hierarchy in memory. I will tell about it very soon, but first I would like to start with the basic computing model that we are using in today's computers and while teaching that algorithms course. Okay, so what do we have? So you see here, we have the CPU, Central Processing Unit. In the good old days, in the previous century, when we say CPU, it was just a single core. So there were no distinction between a core and CPU. But these days, when you purchase a CPU, it comes with multiple cores. Okay, but I will assume a CPU is just a single core, and we'll explain the others a little bit more in detail in the upcoming slides. Okay, so in a CPU, we have the arithmetic logic unit. So that is where your instructions are executed. It is important to understand that arithmetic logic unit can only access to registers. Arithmetic logic unit cannot access to RAM. If you are reading something from memory, it means that that data is first transferred to the registers, and then it is operated. Okay, so that is something important. We'll be visiting that again very soon. And what else we have here? The control unit. So that is the unit that makes the communication with the other parts of the computer. So that is the CPU. And what else we have? We have the main memory. So we have our random access memory chips here. And notice this is an integrated circuit, and main memory is not on the CPU. So it is connected to the CPU with a bus, with a connection, with a wire. And in addition to CPU and main memory, we have the rest. What is this? So these are the disks, screen, keyboard, mouse, whatever you have. We call this the I/O devices. And that is the another part in the main computing model. Okay. So actually, we call this the von Neumann architecture. Okay, so there is the arithmetic logic unit, and that arithmetic logic unit is connected to a memory unit with a bus with wires, and there are some output and input devices connected. Okay, with the RAM model, random access memory model, we assume that the execution of the instructions are sequential. It is one by one, no parallel execution. No instructions can execute at the same time. So this is just for theoretical assumptions that we will be using in the algorithms class. And for the memory, we have unbounded memory of words. Okay, so here we have the words, and word is a chunk, and that chunk can be assumed to be log n for any n value. Okay, we say that this word is of size log n for any n, so you may assume n as the input size for your problem, okay, or the size of the memory, whatever. In other words, that means if you have a memory of, let me say, k bits, then you can retrieve any part of say, m bits from this k-bit memory, and you can access any point of this memory at any time. Okay, so random access is supported, and that's a constant operation, a constant time operation. And what else we have in our simplified computing model? We have equal amount of execution time per instruction. All instructions execute in equal amount of time. And actually, these are not very correct in the real computing environments. And here are the differences. Okay, so first of all, instead of a single core, we have multi-core processors. This is the CPU, and you see in this CPU, we have multiple cores. Okay? And even we can have multiple processors as well. Okay, so each core has its own arithmetic logic unit, and it has some levels of memory. So we call this the L1 and L2 caches. The cores in a CPU, they share another cache. So with the cache, we mean some small amount of memory. And despite this L3 cache, we have the outside the chip memory banks. Okay, so these are DRAMs. Unlike the theoretical assumptions that we have here, so we have some different things happening in real life. First of all, there are some parallel execution possibilities. Not everything is sequential. Since we have multiple cores, and even despite the parallel execution, so these are some high-level things. Okay, so there is an out-of-order execution, which means your instructions 1, 2, 3, 4, 5, 6 may be executed in a different order. Another difference between theory and practice is that, so we assume that we have an unbounded memory of words, but this is not correct. We have limited memory, and those words are not variable size, they are fixed size. So you say that, okay, so that's a 64-bit machine, 32-bit machine. Okay, so the word size is fixed, and you cannot make it variable in real world. Access to memory is assumed to be constant in the theory, but actually it is not constant in the practice. We will be talking about this on the next slide. And surely there are different amount of execution times per instruction. A multiplication is not equal to an addition. Okay, so these have different timings, but for the sake of easy understanding, in the theoretical model, we assume that all are same. Okay. Now let's focus more on how data moves between different levels of memory hierarchy. So here, you see the memory hierarchy. Okay, so at the top, we have the registers. These are the registers that the arithmetic logic unit can access directly. Okay, so these are the registers. And then after the registers, we have L1, L2, and L3 caches. L4, that is a bit rare, but we started seeing them now. And after those cache memories, we have our normal random access memory. So these are the DRAMs actually. And then following that, we have the SSD, HDD, hard disk drives, and then we have the internet. Now I would like to show you how we operate on data. So let's assume this is my core with a single core, and let's assume this is my arithmetic logic unit. When an instruction needs to operate on data, that data should be on the registers. Okay. So when the instruction is being executed on this arithmetic logic unit, it first checks whether the data is ready on the registers. If data is ready on the registers, so they can just access it and do it very fast, lightning fast. Okay, so this is the first level. What if the data that you will operate on is not ready in the registers? Then that means it should be moved from the random access memory, RAM, to those registers. And that happens in that way. First, if it is not in the registers, the computer goes to L1 cache. Okay, L1 cache is a bit larger than the registers and says, okay, so do you have this data ready for me? If it is in L1 cache, it is copied to registers and it is done. If not, then we go to the big main memory. Let's assume it was not ready in registers L1, L2, and L3. So, and I would like to access the data here. Okay, actually, I only need this data point. But remember, the locality of reference principle. It means if I am operating on this data point, then I will need this data again. So it will be best for me to keep this closer to the CPU as much as possible. That is the temporal locality of reference. What was the second locality of reference? It is the locality of reference in space, which means if you are accessing that data point, it is likely that you will be accessing the near points very soon. That is why, while carrying this data to the register, we do not only carry itself, but we carry it as a package. Okay, so we first move this data from main memory to L3, and then copy from L3 to L2, and then the L1, and then we move the regarding point to the register, and we are done. Okay. So that means actually what I would like to emphasize is while moving your data between the different levels of the memory, it is not a singular atomic operation. Okay, so you are moving data in chunks. That means if your data is maintained in the memory as a contiguous block, then that will be very beneficial for further operations. With the beneficial, I mean it will be very fast. I need to say that, okay, so the fastest level of memory is the registers, and L1 is a bit slower than registers. L2 a bit slower than L1. L3 it's a bit slower than L2. And main memory is a lot more slower than those cache levels. That is why it is very beneficial for the sake of fast response to keep data as close as possible to the CPU. Okay. That is why we have these levels of memory hierarchy to support locality of reference in computer architecture. Okay. So after those explanations, let's go with the arrays. So what is an array? Actually, you all know this, okay? So we are just remembering what we already learned before, okay? So an array is a contiguous block. So that is very important. Okay, so if this is my memory, my array resides as a contiguous block here. So let's assume it is this one, okay? So this is the starting address in the memory. And you see that each compartment, each item in the array has the same length. So if these are the byte addresses, okay, so 200, 204, 208, each item is 4 bytes long. Very good, okay. That is very good because if I would like to reach let me say the fourth item here, if we start from 0, it will be the third. The index will be 3. If I would like to access the fourth item, then the only thing I need to do is I will go to the starting address and advance this address how many times? 3 positions. Okay, so 200 plus 3 times 4. Okay, so this will give me 212. 212 is the starting position of the fourth item of this array. That means when you are using an array, you can access any random position with just one address calculation. Okay, so that is important because arrays are very beneficial because they support the random access in constant time. However, you know that if you would like to insert or delete something from the array, it's not that much easy. Again, assume this is my array of size, let me say 10, and I would like to make it 11. I cannot simply say that, okay, please extend this one more position. That doesn't happen. So that has a long stories behind, but I will skip it. What happens if you would like to resize your array? So another memory location, let me say with 11 items, so it is reserved, and all these guys are moved to this new location with the additional one at the end or somewhere in between. So that is why if you would like to insert or delete something into an array, it causes a lot of operations at the background. So that is why arrays are not good for insertions or deletions, but they are very good for random access. If you would like to access the kth item in an array, you can compute its address immediately and you can go and read it from there. Okay. Okay, so it respects the locality of reference a lot, particularly the locality of reference in space. So let's have a couple of words here. Why? Because you are maintaining an array, and let's say this is the array of student IDs, student cards, whatever. Okay, so remember the locality of reference. Locality of reference says if you are accessing this position, then you will be accessing the near positions of the recently accessed one very soon. Since in the memory hierarchy, you move data in chunks, that means when you read this data, you will be already moving the data nearby, very close to your CPU. And the next time, according to this locality of reference, if you need a nearby item, you will go and find it in the upper levels of the memory. That is why it is very good, and actually array data structure is the most widely used data structure in programming. I guess you already noticed that with your previous experience. Okay. The second way to represent data digitally in memory is linked list. This time, what I would like to do is I will not be storing it as a contiguous block. Let me again try to sketch it. So this is my memory. Okay, I will say that, okay, so I will keep my first data point here. So let's say my data 1, and then I will have data 2 here, and I will have data 3 here, maybe data 4 here, okay? What it needs, if I would like to traverse this data, I will start with the first one. Assume I know this, its address, okay? When I go to first data point, how will I know where is the next one? Because it's not contiguous, right? Since it's not contiguous, I need to know the address of the next position. That means there should be an additional field, so we call this a link for the next guy. Similarly, next guy has another link, to the following, and that continues until the last one, which says that I don't have any followers. Okay, so that's called a linked list. So let's see what is good with linked list. Let's assume you would like to insert something between D2 and D3. Very easy. You can just allocate some memory, some space in memory. So let's say that is D5. And you say that, okay, so what I will do is I will update the links. Now D2 will point to D5 and D5 will point to D3, and you will be erasing that link. Now it's easy, right? So you don't need to move all the other elements. However, to make this insertion, you need to go to the appropriate position. That means if you would like to go to the kth element in a linked list, you have to start from the first one and follow the links one by one, one by one. So that is the downside of the linked list. You cannot perform a random access. If you would like to access the kth item, you have to follow the previous k-1 links. On the other hand, if you are maintaining your data with a linked list, then you can make insertions and deletions a lot easier. There are many different types of linked lists. So we have the single linked list, we have the double linked lists, and circular linked lists. Okay, so actually the names are very descriptive. If you have the single linked list, then you can go to the next data point, but you cannot go to the previous. So if you maintain two links, two pointers per each data point, then that means you can go back and forward. You can go to next, you can go to previous. Okay, and what else I can say? So while implementing those linked lists, particularly while making the insertions and deletions, so you should be very careful. I guess you might have already did some examples in your previous programming classes. So if you do not update the links appropriately, so you may get totally lost and mess up with everything, and you can lose your access to the remaining of the list when you do an insertion or deletion. So those are a little bit tricky parts while implementing a linked list. Okay, so we have the arrays and we have the linked lists. To understand the array and linked list data structures and to compare them, I highly suggest you to study two different problems. Okay, so the first one is the range minimum queries, and you can study this on arrays with the range minimum query. What we mean is, okay, so you are given an array of integers, and there is a dynamic range. So the query tells you that, okay, please tell me the minimum element starting from position 5 to 11, let's say. And you may have different queries like that. How can you find the minimum in a queried range efficiently? So that's a good exercise to understand the arrays. And another thing, another data structure is the skip list data structure for linked lists. If time permits, maybe we'll have another video for the skip list, but it is, again, highly recommended to remember your old knowledge. Okay, so for the linked lists. Okay, I guess that is all I would like to tell you about these two basic data structures. On the next video, I will try to cover the stacks and queues built upon arrays and linked lists. Okay. Thank you very much, and see you on the next video.